The other problem has to do with the dimension of this matrix problem. Here E times the unit matrix, A equals to 0, or as the eigenvalue problem. This matrix is very, very large. Millions of elements, I mean millions of rows times as many columns. So it's of millions squared elements. And you have to, if you want to do that with a normal linear algebra routine, solve linear equations or eigenvalue problems, you have to store the matrix in memory. And you will not be able to do that. But small systems, yes, large systems, no. So how to do that? That is called direct configuration interaction methods. What you do is you actually never generate the whole matrix. You can see, I mean, what you do is you don't set the matrix up, you don't do an eigenvalue problem with the full matrix. But what you do is you say, okay, these coefficients, which are eigenvectors, I expand that in a basis again. I expand those in some kind of basis, what I want to call it, I. Some basis vectors, bi, with some coefficients. So in a way I do the same trick as I did with Schrödinger equation once again. The unknown, which is here the vector, I expand in a basis of known vectors. And the trick, of course, the idea is, of course, that the number of vectors I use here is much smaller than the dimension of these. Then I can insert that up there. So I get a sum here. I can pull it here, sum over I. I get my basis vector, or trivectors, and a coefficient. Still being 0. And then I multiply from the left, which is basically the same as deriving the Hartree-Fock equation. I multiply with another of those basis vectors. So bj vector, and then obviously that has to be transposed. If it comes from the left, and then I get a sum over I get bj transposed, I get my big Hamiltonian matrix like this, bi ci equals to 0. So I get something here which looks like having this basis vector times the Hamiltonian matrix times another basis vector. And you can see, I mean, that is a quantity. That's again a matrix. That is sort of the ji element of the Hamiltonian matrix, but now in the space of those trivectors, which is called the reduced space. And that might be a few hundred. I need maybe a few hundred of those basis vectors in order to expand this vector. So that dimension is then a few hundred times a few hundred, or maybe a few thousand if it really goes bad, times a few thousand. So it's much more smaller. So in that reduced space, I can solve the eigenvalue problem because I can keep that matrix. I can't keep the original one. Now, that of course doesn't solve the problem. I need to do this matrix product here. But that's not actually done. What is done is I immediately calculate the product of the Hamiltonian matrix times this trivector. So what is implemented in the programs is not calculating of the full matrix, which then would be multiplied on one basis vector, but what is implemented is directly the result of this Hamiltonian matrix times a basis vector. So I only have a column which I have to keep. So in this way we can do those large calculations, because we never would be able to do it in the original way.